I want you to imagine that you're trying to cook a really complex, like 5-course meal.
Okay, sounds stressful already.
Right. But instead of just knowing the recipe, you have someone standing right over your shoulder.
Oh, no.
And they're reading every single instruction to you, like step by agonizing step. They're whispering, pick up the knife, move it over the onion, press down, turn the stove to medium.
Yeah, you'd have absolutely no intuition for the task in that scenario.
Exactly. It technically works, but it's utterly exhausting. The latency between steps is just maddening.
Right, because you're just a blind executor of immediate commands at that point.
Yes, and honestly, you're probably going to drop the onion because you're so hyper-focused on the voice in your ear instead of the natural rhythm of cooking.
You're completely lacking any awareness of the broader context of the meal you're trying to prepare.
And that exhausting step-by-step cooking scenario, that is exactly how the entire tech industry is currently building AI agents.
It really is, yeah.
So today's deep dive is focusing on a state-of-the-art Gen AI paper. It's titled Compiling Agentic Workflows into LLM Weights. We're pulling an excerpt from a curated collection of foundational Gen AI papers for this.
And it represents a profound shift in how we think about imparting procedural knowledge to AI.
It totally does. Our mission today, for you listening, is to explore this radical new approach that completely challenges massive industry trends.
Definitely.
We're going to find out how compiling procedures directly into an AI's brain, meaning its weights, instead of telling it what to do step by step, could make AI hundreds of times cheaper.
And surprisingly, a lot more reliable, too.
Right. So, okay, let's unpack this.
Yeah, so to really grasp why this paper is so revolutionary, we first need to look at the status quo.
The way things are currently done.
Exactly. We have to understand the massively popular way developers build these agents right now, because the researchers argue it's fundamentally flawed.
How so?
Well, currently, the entire software industry is obsessed with what we call agent orchestration frameworks.
Okay, yeah, so these are the big names you see everywhere, right? Like LangGraph, Crew AI, Semantic Kernel.
Precisely. And combined, those orchestration frameworks have amassed over 290,000 GitHub stars.
Wow.
Yeah, they're the undeniable industry standard, and they all follow the exact same architectural pattern, which the paper calls surface orchestration.
Surface orchestration. Okay, what does that actually look like in practice?
Basically, they use an external software orchestrator that sits like a giant middleman between you, the user, and the large language model.
Like the guy reading the recipe.
Exactly like that. Every single time you type a message to the AI, this orchestrator steps in. It evaluates where you are in a predefined flowchart, injects a massive block of instructions into the prompt,
Right.
and then it asks the AI to make a routing decision, parses the output, and only then hands a response back to you.
So the AI never actually learns the process.
Nope.
It just reads a tiny fragment of a manual over and over again for every single interaction.
Yeah, it's highly managed and honestly, incredibly inefficient. And what's fascinating here is that this method is phenomenally resource heavy.
Because of all that constant prompting.
Exactly. The orchestrator has to remind the AI of the specific rules at every single turn. That eats up a massive portion of the model's context window.
Ah, I see.
So this forces you to use massive, expensive, cutting-edge frontier models just to handle basic conversations without the AI completely losing the thread.
Which is incredibly expensive for businesses, right? They're forced to send all their proprietary business logic out to third-party API providers every single time a user sends a message.
Wrapped up inside those massive prompts, yeah.
Which brings us to the alternative presented in the paper. They call it subterranean agents, the subterranean shift.
Right. So the researchers propose entirely removing that external middleman at runtime.
Just getting rid of it.
Getting rid of it. Instead of injecting instructions at every step, you take your procedure, say, a massive flowchart of how to handle an insurance claim, and you use an orchestrator just once.
During the training phase.
Yes. You use it to generate thousands of synthetic conversations that perfectly execute that flowchart from start to finish.
Okay.
Then you take a small open source model, something really lightweight, like an 8 billion parameter model, and you do a full parameter fine-tune on that synthetic data.
So you essentially bake the procedure right into the physical neural pathways of the model.
You compile the workflow directly into the model's weights.
Wow.
So at runtime, the orchestrator is gone, the user talks directly to the small model, and the model just natively knows how to navigate the procedure.
Because the structure is deeply internalized.
Exactly.
So using our earlier analogy, orchestration is like a theater director standing off stage, right? Constantly whispering the script and the stage directions to an actor, line by agonizing line, while the play is actively happening.
Right, which sounds terrible.
But the subterranean approach is just letting the actor memorize the script before the curtain even goes up. They just know where to stand and what to say.
That is a brilliant way to visualize the difference in latency and flow.
Wait, I need to stop you there, though.
Sure.
Because if I look at the numbers, I see a huge red flag.
Okay, what is it?
If this memorization technique, this subterranean approach, is vastly superior, why isn't everyone already doing it? Like, the paper notes that previous compilation papers only got about 3,000 GitHub stars combined. Compared to the 290,000 for orchestration, what are developers so terrified of?
Well, the researchers identified 3 massive perceived barriers stopping developers: quality, cost, and flexibility.
Okay, bring those down for me.
Developers automatically assume a tiny local model will be hopelessly dumb. They assume the cost savings won't be worth the engineering hassle.
Yeah.
And they assume that updating a baked-in model when a business process changes will be a total nightmare.
Let's start with the first one then, the quality paradox. Because the most obvious fear for you listening right now is that if you abandon a massive API model for a tiny 8 billion parameter model running locally, the AI is just going to fall apart.
Right. People think it's going to hallucinate wild answers or fail to follow business rules.
Exactly. So what did the data actually show?
To address that fear, they set up an incredibly rigorous testing ground across 3 domains of increasing complexity.
What were the domains?
First, travel booking. That had 14 flowchart nodes and 3 decision hubs.
Okay, fairly straightforward.
Then Zoom technical support. Also 14 nodes, but this required deep, product-specific domain knowledge.
Like knowing nested settings menus and specific error codes.
Exactly. Complex troubleshooting paths. And finally, they tested the absolute gauntlet insurance claims processing.
Oh, wow. Insurance. That's got to be complicated. 55 complex nodes, right. And 6 different decision hubs.
With nested loops, yes. That is a massive, highly sensitive procedure to trust to a tiny model.
It's a massive cognitive load. So how did they evaluate it?
They generated 200 distinct, highly complex scenarios per condition. They actually used Claude Sonnet 4.5 to act as a dynamic user.
Simulating things like a frustrated customer.
Yeah, or someone providing really vague, unhelpful details.
Yep.
And they also used Claude as the judge to score the conversations.
Wait, isn't there a risk of bias there? Like Claude just preferring its own synthetic style of outputs?
Great point. To ensure there was no inherent bias, they completely verified the robustness of the results, using GPT 4.1 as an independent third-party judge.
Smart. Okay, and I am looking at the results here, and they totally bust the myth that smaller always means dumber.
They really do.
In a controlled apples-to-apples test using a tiny 3 billion parameter model, the subterranean compiled version outright beat the orchestrated version of that exact same 3B model.
On 4 out of 5 quality metrics: task success, consistency, graceful handling of user errors, and naturalness.
And when they scaled up just slightly to an 8 billion parameter compiled model for the Zoom and insurance tasks,
It achieved 87 to 98% of the absolute quality of the massive frontier model, acting with full orchestration context.
that is wild. A tiny 8B model effectively held its own against a Landgraph orchestrator, utilizing a model roughly 70 times larger.
And if we connect this to the bigger picture, these smaller models aren't just holding their own. They are actually failing less often than the giant orchestrated models.
Wait, really? The massive models failed more?
Yeah, the failure rates are incredibly telling. In the travel domain, the massive Landgraph orchestrator had a failure rate of 24%.
It just lost the thread a quarter of the time.
Exactly. And the tiny subterranean agent, its failure rate was only 5.5%.
Wow. What about the massive insurance one?
In the insurance workflow, the orchestrator failed 17% of the time. The tiny compiled model only failed 9% of the time.
The specific anecdotes they included from the source material are honestly hilarious, but they highlight exactly why this structural difference matters.
Oh, the Zoom one is great.
Yeah. In the Zoom support test, the orchestrated model got so utterly bogged down by the massive prompt template being injected at every step
Right.
that it literally suggested the user turn on original sound for musicians to fix a basic audio drop.
Which is terrible advice for a standard corporate meeting. That setting completely disables all background noise suppression.
You'd hear every keyboard click and siren outside.
Exactly.
And in the insurance claim scenario, the breakdown was even worse. The massive orchestrated model got hopelessly confused deep inside that 55-node workflow.
Yeah, it completely lost its place.
It failed to answer a basic question about gap coverage, and then completely unprompted, it hallucinated a handoff to a quote-unquote senior specialist,
It literally outputted a markdown formatted handoff summary to the user.
acting like it was talking to a coworker that didn't actually exist anywhere in the system.
It's absurd. Meanwhile, the tiny subterranean model developed this highly effective organic interview style.
Because it had internalized the training data.
Exactly. It learned to ask one clear, clarifying question per turn. It would ask, wait for the user to respond, and then continue naturally.
Whereas the orchestrator constantly overwhelmed the user.
Right, by spitting out 4 or 5 bullet points of suggestions all at once, because it was just blindly reading the current step of the manual.
Here's where it gets really interesting to me. How on earth does an 8 billion parameter model fundamentally outsmart a frontier model when it comes to failure rates?
It's a great question.
How does a model that small even have the capacity to remember a 55-step insurance claim without hallucinating a ghost manager?
It really comes down to understanding the mechanics of why orchestration fails. Orchestration fragments reasoning.
Fragments it.
Yeah. When a traditional orchestrator is running, it generates a response based only on the specific local node template it's currently sitting on.
So it lacks true global conversation awareness.
Exactly. It forgets what it tried 3 steps ago because that information isn't in the current prompt injection.
But the compiled model is different.
The compiled model reasons over the full procedure holistically. Because the structure is physically baked into its internalized weights, forming what we could call statistical instincts, it naturally flows through the conversation.
With full subconscious awareness of the context.
Right. It doesn't experience routing failures because the routing logic isn't a rule it has to read. It's an instinct that has developed.
Okay, I am entirely sold on the quality. But if these tiny models are solving incredibly complex tasks without needing a massive orchestrator calling a massive frontier model every 10 seconds, the compute requirements must just plummet.
Oh, absolutely.
Which brings us to the second barrier developers fear,
Yeah.
cost. For you listening, if you're managing a budget or just looking at the economics of AI, what does this subterranean shift actually do to the wallet?
The financial breakdown is nothing short of staggering. They found that compiled models are 128 to 462 times cheaper per conversation than the baseline.
462 times cheaper. That is a fundamental change in unit economics.
Yes. Let's look at that massive 55-node insurance workflow. Using an orchestrated frontier model, the cost was roughly 33 cents per single conversation.
Okay.
Using a subterranean agent, that cost plummeted down to less than 1/10 of a cent, $0.007 per conversation.
That's insane. How exactly do the mechanics of those savings compound to get a multiple that high?
It's a powerful 2-factor multiplier. First, you get a massive per-token cost reduction, roughly 65 times cheaper right off the bat.
Because you aren't using an API.
Exactly. You're self-hosting a tiny 8B model on commodity GPU hardware. Instead of paying premium API rates, you can rent a standard reserved A100 graphics card.
Got it.
You then use optimization tools like VLLM, which acts as a highly efficient carpool lane for processing requests. It batches multiple conversations together simultaneously.
So the hardware is never sitting idle, completely bypassing the massive API tax. That makes sense. You own the hardware time.
Right. But the second factor is just as crucial, token volume reduction.
Because you aren't injecting giant prompts anymore.
Exactly. When you use surface orchestration, you're stuffing a giant procedural flowchart into the system prompt over and over again. That consumes a massive amount of tokens.
But a compiled model's prompt is constant size.
The prompt is essentially just, you are a helpful assistant. The procedure is in the weights, not the prompt. This gives you an immediate 2 to 7 times reduction in the sheer volume of text the model processes.
So the more complex your workflow gets, the more money you inherently save by compiling it.
Exactly.
It's like the difference between paying a lawyer's exorbitant hourly rate to sit there and reread the exact same 50-page contract from scratch every single time you call them, versus just hiring an in-house expert who already knows the contract completely by heart.
That is a perfect analogy. And people often worry about the upfront cost of generating that initial training data.
Oh,
right?
sure, the synthetic data.
But the paper shows the total setup cost to generate the data and fine-tune the model is only about $50 to $80.
That's it.
That's it. With the massive reduction in per conversation costs, you break even in less than 500 conversations.
Wow. If you're running a business at any kind of scale, 500 customer service chats is a quiet Tuesday morning. Okay, so we've conquered quality, and the economics are undeniably brilliant. But here's where my mind goes next, and it leads us directly into the third barrier. Workflows change.
They do. Real life isn't static.
Right. Airlines update their baggage weight limits overnight, software gets a totally new user interface, state insurance laws change.
Yep.
If I bake my company's specific procedure deeply into the actual brain of this model, and my boss changes the procedure tomorrow, aren't I stuck with an AI that confidently gives out completely outdated information?
That is the fear, yeah.
Don't we have to go through a massive, painful, world-stopping retraining process?
That is the ultimate psychological hurdle for developers.
Yeah.
They have PTSD from the early days of machine learning, where training a model took weeks of time and millions of dollars.
Right.
But the reality check presented in the paper completely dismantles this myth of inflexibility.
Walk me through it.
Let's break down the actual time it takes to update a subterranean agent. First, data generation. You update your flowchart and use parallelized API calls to rapidly generate a whole new batch of synthetic conversations.
How long does that take?
About 15 to 30 minutes.
Okay, that's incredibly fast. Go grab a coffee and the data is ready.
Next is the full parameter fine-tuning. If you're an enterprise with a heavy-duty server setup like an 8x H200 cluster, pushing that new data into the model's weights takes 10 to 15 minutes.
What if I'm not an enterprise, though?
Even if you are a scrappier developer renting a single standard A100 GPU, it only takes 3 to 4 hours.
Okay, still very reasonable.
Finally, you run your automated evaluation spot checks, which takes another 5 to 15 minutes.
So on standard production hardware, the total time from the moment you update your flowchart to having a fully deployed, newly educated model is roughly 30 to 50 minutes.
Right, and this raises an important question. Why on earth do we continue to treat fine-tuning an AI as a massive world-stopping event?
Because it used to be.
Exactly. But in traditional software engineering, we compile code multiple times a day without a second thought. This paper proves that compiling an AI agent is really just a standard CI/CD cycle, continuous integration and continuous deployment.
So we just need to shift our perspective.
Updating a model's weights is just a completely normal deployment shift. It is not a terrifying paradigm shift.
So what does this all mean? For you listening, whether you're managing a customer service team, building a startup, or you're just endlessly curious about AI engineering, this fundamentally changes the roadmap.
It really does.
You don't need to be handcuffed to expensive, sluggish, external APIs for static procedural tasks anymore. The state of the art is telling us loudly and clearly that persistent structure belongs in the model's weights.
And only transient state, meaning the immediate, messy back and forth of the current conversation, belongs in the prompt.
That's a foundational separation of concerns.
One that the traditional software industry learned decades ago, yeah. And it's finally being properly applied to generative AI. We've been treating these brilliant language models like highly amnesiac, stateless functions.
That need to be aggressively reminded of the basic rules of their job every 10 seconds.
Right. But by imparting procedural memory deeply into their weights, they transform into highly specialized, instinctual agents that are exponentially more competent and incredibly efficient.
So to wrap up what we've unpacked today, the dominant industry trend of surface orchestration, putting that heavy middleman between the user and the AI, is massively expensive.
Yep.
It's incredibly prone to brittle routing failures, and it forces a stiff, robotic conversational style. Compiling those workflows into subterranean agents, however, delivers near-frontier quality from tiny local models.
It slashes compute costs by over 2 orders of magnitude.
And the procedures can be fully updated on your lunch break.
The perceived industry barriers of quality, cost, and flexibility simply collapse when exposed to the actual engineering data.
They really do. And I want to leave you with a final thought to mull over. Think about all the incredibly complex, completely static processes in your life or your workplace.
Oh, there are so many.
Human resources intake manuals, technical troubleshooting guides for your car, convoluted legal forms, even the repair steps for your refrigerator.
Right.
If we can cheaply compile complex procedural knowledge directly into the structural instincts of tiny, local AI models, what happens when every single app, every physical appliance, or even your local offline home network has its own hyper-specialized expert baked right into the silicon?
It's a huge shift.
Are we rapidly moving away from an era of prompting massive, expensive oracles in the cloud and moving into an era of deploying millions of cheap, deeply instinctual specialists right in our pockets.
Instead of a stress director constantly whispering instructions from a server hundreds of miles away.
Tomorrow's AI might just be a cast of perfectly rehearsed actors, ready the moment the curtain goes up. Thank you so much for joining today's deep dive, and as always, keep questioning the status quo.